Hello everyone. I'm sure you're doing awesome. So this is another video on the networking internals for the application developers. So today we are going to discuss in detail about the TCP and its real life use cases. In the earlier video, we have detailed out around UDP and why we need it. And there also we touched upon in our initial videos a couple of things regarding the TCP, but this video is particularly dedicated to that and understanding TCP and its profound implications on the system design, the performance and the reliability, security. We are going to deconstruct all of this thing in super detail. So let's try to see on a very basic level what is the latency and where exactly the TCP comes in play in this for any networking calls. Okay, so suppose there is a mobile banking app in London. There is a mobile banking app user in London who is making a call to the Bank of Singapore. Okay, so probably that person is a citizen of Singapore. He has traveled to London and he is making a call to the server in Singapore. And this is a latency sensitive operation. So when we are saying it, this is a operation. But why? So let's try to understand it in terms of the generic physics and maths. Okay. So when we are talking about the network latency, we talk about RTT or the round trip time. So how much time this particular request would take, that it will go here and then again the response will come back. So the request and the response. So how much time it takes, that request plus response cycle is known as round trip time. Okay. So now the question is, how much time will be required for a RTT or the round trip time for this mobile banking app for this given request? So if we are using optical fiber as our internet connection, so we can say theoretically the data goes in a speed of light, that is 200,000 kilometer per second. And if I'm just keeping the distance between the Singapore and the London, that is around 10,900 kilometer. So in a one way it will be around 55 millisecond. So if I divide 10,900 kilometer by 200,000 kilometer, it is coming around this. Okay, and so I can say that minimum possible delay, so we can just mention like this: the minimum possible delay due to physics of data transfer is how much here? 110 milliseconds for this given request. Okay, so there will always be a latency whenever we are sending a request and we are getting it. Okay, now this is a very foundation of the TCP. Why? The request that is being created over here, if this is a TCP request, TCP happens in a three-way handshake mode. Okay, so I will just write it down and then explain. TCP happen in three-way handshake mode. So how is this? Let's discuss it further. Now during this interaction of three-way handshake, the thing that we need to remember is TCP is the prerequisite of any sort of request response that is happening across the internet. Okay, so TCP is the first thing that is need to be established across, then only the rest of the requests will go. So for example, in this case, okay, suppose the mobile banking user is making a request something like get balance. Okay, so even before get balance, the TCP connection needs to be established. Okay, so just remember this part, that TCP is the prerequisite of this. And let's see what happens when we talk about a three-way handshake and how much time it may take. Okay, so when we are talking about the three-way handshake, the client or the mobile banking user, when it is trying to create the connection, the first thing it send is something called a SYN flag, SYN. Okay, so what happens during the SYN flag? SYN flag simply tells that I want to connect, and it also shares a certain sequence number. That sequence number, suppose it tells that my sequence number is 100. Okay, so once the server receives the SYN, what it does is it sends back SYN-ACK. Okay, so here what exactly the SYN-ACK means? It is the response of the server. It says that okay, I am in for the communication. My starting number is 300 and I acknowledge your 100. So exactly this sort of communication keep on happening in a different byte format internally. So now what would happen is the client then have to tell the server back that I have received your 300. How it will tell? It will now send a ACK. So the first one is basically, if you see, it is a SYN, and the second one is SYN ACK. And what is the third one? The third one is ACK. In the ACK, we are going to send that I got it, let's connect, I ACK what 301. So one of the important thing is here you see I acknowledge your, it will be 101. Okay, so it just increments the connect, it increments the sequence of the connect request, and it sent the next one. So it acknowledges 101 and sends acknowledges 100 and sends 101, and here it acknowledges 300 and send back 301. So when this whole process happens, like if you see this thing, once this whole process happens, this thing is being called the three-way handshake, because you can see SYN ACK and the ACK that happens across. So the total time, if I have to calculate, what happens over here is, if my physics says 110 for these two requests, and then another ACK will go, so it will be somewhere around 55 more. So total it is becoming somewhere around 165 millisecond. Okay, so this is the time, and also some additional time for uh, processing might also be there, but this is the minimum time that we are looking here for a single request event to get started off. Okay, so this get balance or anything that event to get started off, this three-way handshake has to be there at the initial level. So now just understand one thing intuitively. So after get balance, suppose I want to do something like, so get balance is my first thing. So after get balance, I want to do something like a transfer. Then I want to check my bank statement. Now you probably understand one thing, that if every single time that TCP has to be established before every single call, for example, here the get balance call is there, after get balance the transfer call, after that this bank statement, for every single time there will be a overhead of 165 millisecond minimum, plus there are other processing is involved as well. So that will be a good amount of lead time there. So in TCP, one very important concept that is being used is called keep alive. Okay, keep alive. So what exactly keep alive is? Keep alive tells that this particular connection that you have created, you can keep it alive, and all the subsequent things such as the transfer, bank statement, or whatnot, the rest of the operations that are happening, all the REST API calls that are happening after the initial TCP connection, you can use the same TCP connection throughout. Okay, so that is the idea of the keep alive. So what is the main takeaway out of this discussion right now? That there is a, for any service communication to happen over the internet, if it is happening as a REST communication or representational state transfer where the generic API calls are happening, a TCP connection has to be established, and TCP is a expensive operation. Why? For TCP, there has to be a SYN-ACK, and the ACK that has to be completed for the connection establishment, and there is a certain physics involved. What is the minimum possible delay for this connection that will be there? So now, probably as a developer, you might be wondering what exactly this keep alive. That I understand that this connection establishment is happening, and all the subsequent calls like transfer, the bank statement, and whatnot, everything will go uh, by using this connection only. And how can I leverage keep alive? So as a developer, this is definitely one of the point of interest for us. So keep alive is basically controlled via the connection header in our HTTP request. So the I will just write it for the clarification. For a HTTP request, in the connection header, we send this as a param or as a flag, we can say. Okay, so uh, let's make it simple for us right now. We use this as a flag, the keep alive flag, we can say. So what exactly happens there in HTTP 1? So probably you might be aware that there are multiple HTTP versions has been there, like HTTP 1, 2, 3. So in HTTP 1, what used to happen is, if we do not send keep alive, uh, if we do not send the keep alive, it used to closed after each response. So the developer, like as a developer, our takeaway would be, in every HTTP call that we are making, we have to make sure in our payload or in our request, we are sending the keep alive flag. Okay, we are sending the keep alive flag, and it will look something like this. Like if we just see, the connection is basically the keep alive. Okay, and if we are sending keep alive, that means the subsequent connection won't close for HTTP 1. But the good thing was, in the HTTP 1.1, when the internet community found out that this is one of the important most important flag across the communication, so it was enabled by default. And what we have to do, if we have to close it, then at that point of time, instead of keep alive, we have to mark this thing as close. Okay, so we have to, out of our own enforcement, we have to apply the close. Whereas in the HTTP 1, what used to happen is, after each response, like for example, after get balance, if I do not pass keep alive, then the connection would have been closed, and again in the next connection for the transfer, again the TCP connection would be has to be established, and then the REST API will be able to communicate among each other. Now, as a developer, from the client code also, we should be very wary of on reusing these connections. So for example, in Java, if we just see this if we just see this example, you see, in every time we are reusing this connection. We are setting that how many connection it can create, and the same connection again and again we will keep on creating. So the client, this client that you are seeing over here, this client we are going to use not only for this request and even for all the subsequent requests. In that way, once this TCP connection is being created, so this is basically TCP creating the TCP connection and persisting. So the idea over here is using this TCP connection and persisting it, we are making sure the connection instance is not created again and again, and we are reusing it. And trust me, this is a very expensive operation from the application perspective as well, because every time you will be doing this three-way handshake, so the application will take way more time than 165 milliseconds that we talked about, because there are some other latencies would be added. For example, how your operating system kernel or your NIC, the network interface card, everything handles this thing. So please understand, this is a very, very important best practices. As a developer in the client code, we always write the code in a way that we reuse our connections. Okay. And other than that, also one important thing is that even if the client supports it, also the server has to allow the persistent connection. So here we have this server, right? So suppose in my mobile banking here, in my mobile banking here, I have persisted the connection in this way. But if the server doesn't support, I will write it here, although client persists the connection, if the server doesn't support keep alive, then there is no way we can reuse it. So for example, in Nginx, okay, in Nginx there is a certain parameters like the keep alive timeout, the keep alive requests. You can just study all of them on your own interests. So the point I'm trying to make is using the client and the server, both of the setup, we have to make sure that we are using TCP optimally, and we are not wasting our connections or our RTT time. Okay, so we have uh, discussed a very important concept here, which is keep alive, and this particular concept that we have used over here, talked over here, is known as connection polling. Okay, so this is basically connection polling. So that means like I am maintaining the pool of my connection, I'm not destroying anything. Okay, so this is the kind of like a server setup, and this is the client setup that we have to be very, very careful while writing our application code. Now let's tackle a real life problem which I have seen in my day-to-day life as an application developer. I'm just changing the countries and some other things, but the core of the problem statement is quite same. So suppose there is a users, those are in Australia, they complain that their first product search is quite slow, but the subsequent searches are fast. And the point is, it is probably something, some sort of a big e-commerce. The backend is in Virginia, US, and the API uses HTTP 1.1. So what is likely happening and how would you fix it? So I would request you to just pause the video for a second and go through it. If you don't understand, it is a very simple problem statement, but the core of the but the core of the root cause will give us a lot of insights. So if I just do the simple physics and maths here, the user is in Australia, my backend is in Virginia, USA. The total distance is 15,000 kilometer, and if we just do the maths for the optical fiber, the round trip time will come around 250 to 300 milliseconds. Okay, and plus there are things like the TLS, which we will cover in our next video, and there are some other operating system or the kernel handling of the request. It might be taking a little bit more time. So in that case we will not be able to optimize it in a generic way, because this is a normal RTT, or the round trip time, that it anyway will take for the initial request. But one thing we definitely can do, so once the user log in, we can persist his connection at that point of time only. So what we can do is we can put his connection polled with the keep alive. Okay, we can mark a keep alive, and keep alive we can put it maybe for 2 minutes, 3 minutes, and a little bit more time in terms of the server. So in both client and the server we can give a high keep alive, plus in the we can implement the connection pooling to make sure the initial connection that is being done for the login, we are using the same connection. So here probably we are initiating a new connection for the search and the other backend related thing, and the login is happening from a different perspective. So we can just mix all of them and try to fix this in that way. And again, like, this is what we did when we got the similar sort of a problem, or the complaint from one of our user registries. So this is exactly what we did. We applied a little bit more aggressive keep alive, and we made sure that the connection that we are creating for the login, we are using the same connection for the search or for the any other subsequent operations. Okay, so probably this gives you some idea why this knowledge is very important of TCP while we are even writing a simple application. And also one more thing I would like to bring to your attention is, so over the time when we gradually migrated our application, what we did was we used HTTP 2. So HTTP 2 has some profound advantages over HTTP 1.1. So it uses one TCP connection for all the requests automatically. We do not have to enforce this kind of things. So like for HTTP 2, if we are using, which most of the websites and the servers are using behind the scene, so that uses only a single TCP connection for all the requests, and there is something called the HOL, or the head of line blocking, which we will again cover in our subsequent videos with some detail. That those kind of issues doesn't happen with the HTTP 2. So if you are writing any modern application, just make sure that you are using HTTP 2. And even with HTTP 2, although you do not have to worry about the TCP connection reusing, but as a best practice of the code, make sure at the server end and at the client end, this settings, or rather your connection reuse is been been enforced from the code and the server settings. Okay, so let's get back to the TCP, the other mechanism or the other fundamentals, and how it exactly controls the World Wide Web. So the World Wide Web is basically mostly running on TCP. You have already seen the use cases of UDP in the previous video, but if you see, for the normal REST or the normal HTTP calls, TCP is the main foundation. Okay, so there are two fundamental mechanisms which we will explore in these videos, that is called flow control and the congestion control, and we will also see why these two things are super important and how they are the reason why the internet works so flawlessly. Okay, so flow control, if I just tell on a very high level, what it is it prevents the sender from overwhelming the receiver's buffer. So if you have followed the operating system internals video, you probably remember when there is a machine which is controlling the which is receiving all the requests, there is a certain receiver buffers in that server machine is there. Okay, so you TCP using flow control protects that, and also there is something called congestion control. It prevents the sender from overwhelming the networks like the routers and the links. So flow control, it protects the receiver and this protects the sender. How? We will definitely do a deep dive around it, but on a very high level, these are the two very important fundamental mechanism of TCP that is being done. Okay, so now let's try to understand through a full request response cycle what exactly flow control is and how it is being done. So before going into this, let's try to understand one thing, something called a receiver window size. So what exactly receiver window size tells? Receiver window size is also known as like RWND. Okay, so RWND tells that what is the size of the data I can process. Okay, so it is basically the receiver window size. Okay, now we will just see over here from the client and the server TCP stack how the whole thing is being orchestrated via our receiver window size flag. Okay, so when the first connection that is being established, that we know that there will be a SYN and the ACK that will be going on. So when the first sequence only goes, it tells that I have a window size like RWND size of 64,000. That means like I can receive the data of size up to 64 KB. So now here what happens is, what is the significance is, server knows client can receive up to 64 KB. Okay, and then during the SYN-ACK what happens is, during the SYN-ACK the server sends back that what is its RND window. So when the SYN-ACK goes, at that point of time it tells that my window size is 128 KB. So now the client knows. Okay, here the client knows server can receive up to 128 KB. Okay, so this is the client and this is the server, like they both right now knows what exactly that they will be receiving. Okay, what is the size that they will be receiving, they both are aware of it. So now suppose the first time from the client there is a certain query that is being sent of 10 KB. So a query that is being sent after establishing the connection that is being as 10 KB, and then what happens is the TCP stack checks whether the server has the capacity for that 10 or not. So what it does is it sends the data, and the data packets are sent in this way. There is a certain sequence that is being sent, and with the sequence the length of the data, that is 10 KB, will be basically 10,000. Okay, and what happens is it then delivered to the server and all the processing and everything happens. And while the interesting part is, after the processing, when the acknowledgement comes, okay, so here we are sending the data. After sending the data, when the acknowledgement comes, there it says that currently how much amount of receive buffer it has used and what is the left. Okay, so suppose out of 128 KB, suppose out of 128 KB, in this particular instance already 127 KB is used. So in the ACK what would happen is it will send a number of RWND of 1000. That means the server is telling, the significance is server is telling I can't process anything more than 1 KB. Okay, so this is a clear cut message that the server is sending across. Once the buffer has space, then it sends something called a window update. Okay, so in that case, this is one of the magic sauce of the TCP flow control. It sends the TCP window update, and in the window update it again tell that look, now my RWND variable is 65,000, so I can process up to 65 KB space. Now what would happen is the next query, the query that was going on from here, this query will now successfully will be again sent, and it will be delivered to DB and or the server. And what would happen is, like, here the processing, it would go, and there the processing would happen, and all the data will be again coming back. Okay, so here the processing, here the data would go, and here the acknowledgement will come back. Okay, so now probably you got the idea how beautifully using this receiver window size variable, TCP controls the flow across the internet. So this makes sure, like, in case the server is sending a huge data and the client TCP stack is again telling that I can only receive like 64 KB of data, same thing happens here also, that the server will keep on waiting for the window update of the client. So by the time the client send the window update, then only the server's response will go through. So this is the very core of the TCP flow control, and I hope you got the idea around it. So now our point of interest is how, as a developer, we can control the receive window or RWND variable. So the straight answer to that is we cannot control it directly. For example, earlier we have seen with our TCP header, we can send the values across, right? So here with the TCP header, we cannot really send across the values like RWND and then send it across through the communication. Rather, it is being handled by operating system. So we cannot control the variable directly in our TCP header. Why? Because it is handled by OS kernel and it is not really exposed to the app. And so we cannot really force something like RWND equal to some very big number. And why this thing is not being given to the developer, probably you understand the implication that if it is being given to the developers, there is a chance of miscalculation. Rather, it is being calculated by or handled by the OS kernel. Okay, so also we cannot negotiate this window scale manually because it is handled during the handshake, and whatever the available receiver window size is, the kernel get to calculate that particular value is being sent across. However, having said that, there is something called like TCP receive buffer size, which we can set. This is the most direct way to influence to have the maximum possible RWND. So how does it look like? So here, this is a Python example. In this Python code, you see there is a particular variable that I have set while setting up the socket connection, that is ASO receive buffer. So ASO receive buffer is, in case we are setting into a certain value, what it will do is when that buffer is completely empty and the advertised RWND value will be equal to the buffer size. Okay, so this is basically like we advertise at the time of setting the socket connection, but again when the communication starts, it is the responsibility of the kernel which sets it. So it is very important to understand, although like there is a lot of programmatic way we can do the flow control, like by doing parallelism or by achieving concurrency, but there is no direct way we could influence that. It only depends upon the infrastructure, and the OS automatically calculates that. So that means, like, with a high config machine, it will be definitely high. Okay, RWND will be on higher side. So I think this is pretty much understandable regarding the flow control, whatever the things we can do over here. Okay, so now that we understand what flow control is, let's try to understand another very important aspect. But sometimes we, even the developers, get confused what exactly is a flow control and a congestion control. So I would just like to point out the differences with a single sentence. So in the flow control, what happens is, like, we are telling, don't send me more than I can handle. Okay. So, and what is the variable that is being used here? That is receiver window size. Okay. So with the RWND, we tell that I can only handle 128 KB. That is my maximum I can process at a given point of time. Now coming to congestion control, what happens there is, I am going to tell the network is going to optimize in a way that in a congestion control, we are going to say that don't send faster than the network can handle. As simple as that. So we are going to tell that the network can handle with a given speed. So flow defines the volume, and congestion defines the field. Congestion defines the speed of the network. Okay. So now let's try to understand congestion control with a real world example. So in our example, suppose you and your brother, you guys are in the same house you are staying, and you are using the same internet, right? So using the same internet, you are accessing the Netflix server, and your brother is currently doing very small browsing activities which are not really taking a lot of bandwidth. So the moment you start watching Netflix, what would happen is, like, you make a client request. Okay. So from the client, your request goes to the server, and in the server, uh, the flag or the variable that is being that that is being calculated initially is a very basic number of CWND, or congestion window. So what happens is, CWND will start really small, and for every acknowledgement received, like here is the request goes, and the moment it gets the acknowledgement for this CWND, what happens is, the CWND will increase, and actually it will be like little bit on the other side. So CWND will, so while Netflix is sending the data, it will see how much you can process, and after that you will send the acknowledgement that hey, I can process 10. So in the next, what would happen is, the CWND will be 20. So this is how our CWND, or the congestion window variable, will keep on increasing exponentially. So what would happen is, from 10 to 20, then to 40, it will start increasing. And the moment it experiences any packet loss, it will hover around that that area. So suppose after going like this, around 160 around 160 kb, it experiences packet loss. Okay. So if it is experiences packet loss, then it will kind of stay there only. Okay. Now, so what would happen in this kind of exchanges, over the time, CWND will be sitting somewhere around 150 to 160. Okay, based on when it first experienced the packet loss during the exponential increase of the congestion window. Okay, so this is what exactly a very generic mechanism is. So now suppose there is another character in your in our story over here, that is your brother. Okay, so suppose at that point of time, from small browsing, your brother starts a HD video call with their friends group. Okay, so what would happen is there is a good amount of bandwidth which you are taking. So a part of the bandwidth will also be taken by this, right? So probably you were taking the 80% of the bandwidth previously, now it will be 60% of the bandwidth for you. So now there will be again a division of bandwidth between this between you and your brother. So now what Netflix would see, that even at 150 or 160 kilobyte range there are packet losses. So at that point of time, like when there is a sudden drop in the connection, so I will write it over here in this way: packet loss due to brothers HD video call. Okay, so the moment Netflix sees that there is a certain there is a certain packet loss are happening on a steady traffic, or the TCP connection would see, then what would happen is it again directly halves it. So CWND will be now previously whatever the CWND value divided by 2. So it will be hovering around 80 kb. I'm just making up this number, guys, but this is what exactly will happen over here, that the moment it experiences any packet loss, the congestion window will be marked into half. And again what would happen, so as we were discussing, that every time we get the ACK, this thing it get adjusted, so it will see that whether 80 kb is enough or not. So in between what would happen is, like in this time period you will see, see that there is a little bit of buffer or stutter sort of a thing. Okay, we see this sort of things in our YouTube videos or in Netflix, right? While seeing the video, there is a certain stutter happens at that point of time. This 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 sort of drop happens. Okay, so the moment again we get the ACK, what would happen is again it will be increased. So probably it will again be increased to somewhere around 90 kb. In case instead of ACK again there is a packet loss, then again it will drop it from 80 to again half 40 kb. And our application, as our application developer, we will keep on reading that in what bitrate we are sending across, and based on that what we will do is in our client application, like as an application developer, what we generally do is as a client in our client application we will keep on decreasing, we will keep on decreasing our actual bit rate. So that is the time when like when this kind of packet loss happens. So suppose you are watching a 4K video, from 4K it might suddenly come to 360p because your network doesn't have that much of bandwidth. So now probably you get the idea that what exactly happens in the congestion control, like how beautifully TCP designs the whole congestion to maintain this principle that that one user doesn't monopolize the link. So suppose you are using the internet, and TCP is the connection which makes sure that you are not the one who completely monopolizes your home internet and all the bandwidth. In case there are like your parents, your brother and other person who are in that same home network and trying to access the internet, they will get a fair share of this, and that is being controlled by this congestion control mechanism. Okay, so now let's bring the flow control and the congestion control together. So suppose you as a client, you are reaching out to the Netflix server via your network. So network, as we discussed, like probably just think it as your home network, like any Wi-Fi that you are connected to, or even it can be anything like your mobile network, right? So what exactly happens is through flow control, the client device tells that to the Netflix server that my buffer can hold 1 MB only. So what Netflix decides is that because this particular message it got, so what Netflix decides that through network it will keep on send 1 MB video chunk only. Okay. So here basically the client's limit of processing the data is respected through the flow control. So there is no buffer overflow happens. Now what happens in the congestion control? It happens kind of a client plus the network, both of them together. So Netflix initially to the network will send data with a burst of suppose 100 kb, and it sees that with 100 kb there is no packet loss. So with 100 kb there is no packet loss. So what would happen then? Then it will incrementally keep on increasing it, like from 100 kb it will increase something like, 200 kb. Okay, and gradually it will keep on increasing like maybe 1 MB, and then at that point of time, then suppose around 1 MB or it becomes something like 2 MB, at that point of time it sees that there is a packets lost. Okay, so the moment it sees the packets lost, so then it will start slowing down and it will reduce again to the smaller chunks. So probably it will again come back to 1 MB, then gradually increase to 1.5 MB, something like that. So there is a smooth delivery of the traffic happens. So this deals with the capacity of the client, and this deals with the capacity of the network. Okay, like how fast the network can process the data that it is receiving from the server. So now probably we got the idea how flow control and the congestion control work together. So now let's talk about one more important term, that how exactly the ordering of the packets are maintained. So what exactly the packets we already discussed, we will just try to revisit it again, and what is the importance of the ordering of the packets and how uh, TCP helps the whole communication framework to maintain that particular ordering or the sequences. So let's discuss why ordering is important. So suppose you are going to Google, and in the Google you are searching something like the best coffee, something like best coffee near me. Okay. So what generally Google does is Google will send your query to all of its different servers. Like there are ranking, location, ads, whatnot. It will run every single thing. For example, there is a page rank, there is location, there is ad server. It will run its data through, and then after all of these things, what happens is like there will be a after all of these things there will be a HTML page that will be generated over there. Okay, so now when this HTML is sent back to the browser, the network between the Google's data center and my client device is quite complex, right? So the data travels over the fiber, routers, Wi-Fi, and whatnot. Different packets take different paths. So some paths are faster than others. So suppose uh, like there is a HTML page is getting generated, and there are different parts of this HTML page. Some part is coming from the page rank, some part is coming from location, and some part is again coming from the ad server. Now it might be possible that there is a packet 1, okay, which contains something like HTML head and whatnot, okay, and then there is a next packet 2 which will actually hold the whole body of the HTML. Okay, so when we are looking into it, the first packet is having the HTML header and then the whole packet. And what happens over there is, because there are different network latency across the system, the sequence number, or there is a certain byte stream ordering that is being maintained within this TCP connection. So what happens is, if I have to just again if I'm trying to make you visualize it, it is something like this. So there is a segment A which has all the HTTP details like HTTP 1.1 200, okay, and then the segment B, it has the title of the best coffee, and the segment C, it has the data like best coffee near me, and within the H1 body and the div tags, all the informations are there. So one thing that TCP allows you to do is arriving the packets out of order. So what might happen is, out of order packet arrival at client end. Okay. So what exactly happens over here? So here we have segment C at first. Okay. So segment C, the sequence number is something like 1160. Okay. This is the first one. Then something like segment A. So segment A will be having a sequence number of earlier, because this is the first one. Then there will be segment C, sorry, segment B, and this segment B will have again a sequence number of 1080. So in this case, although it is out of order, but you see the sequence number kind of tells me which one is the first one. So the browser uses this sequence number to reconstruct the byte stream. So it sees that the segment C, and it notes that it starts with byte 1160, and it holds it into the buffer. So this one just goes to the buffer, and then again it when it encounters A, it writes to the stream. Okay, so it writes to my stream, and again once it gets 1080 also it writes to the stream, and then the buffered element, that is the 1160 or the segment C, is again come to the stream completely in order by using the sequence number. Okay, so the result is the page renders correctly, all the sequences are coming in a in a complete ordered manner, and the main part is like my application never know. So although I'm the application developer, but we do not have to worry about this ordering of the sequences. It is just for the knowledge that behind the scene this sort of magic that is being done by TCP. So the application never knows, and it feels although like some rendering feels instant and reliable, but behind the scene this kind of misjudged ordering or like out of order traffic comes, which is being ordered by TCP by using the sequence numbers. So you might be here having this question like, who tells the TCP that the data starts from the 1000? So initially when the acknowledgement related data is being exchanged, at that point of time only, what will be the first sequence that will be sent, those kind of informations are being exchanged. And there is a something called a sliding window of the expected data. So TCP keeps on receiving the sliding window, but I'm not taking into the those things in a scope, but those will be a very good additional read, like how exactly uh, TCP handles all the data through the sliding window, like the ordering of the data and the sequences, everything using the sliding window. So now let's take a look at the application code and what exactly happens in the TCP, and we will try to conclude our discussion after this. So now let's take a look into a Golang code. So over here, uh, a very simple code, what it is doing is, it is reaching out to www.google.com, and whatever the data it is getting back, it is just printing, and in case there is any error that it encounters, it prints that too. Okay, although it is a very simple looking code, uh, but if you see, like if you have understood all the operating system and the uh, networking details that are being employed over here, there are multiple components that are involved. So what are the components that are involved? The first thing is definitely the application that we have written, that is the Go application. Then the Go application is having this HTTP client, which it is using this client, and this is again one of the client libraries are always given by the frameworks only, but we are just keeping it as a separate one because sometimes this is an external framework that is being used in a Go application. And then the operating system kernel, that too has a good amount of role. Okay, that too has a good amount of role. And of course the network. So when I say network, just think it as a home network, do not think the whole OSI layer over here. And then because it is reaching to google.com, there is Google server. Okay, so this many number of components that are being involved over here. So at first, how the connection happens is, from the Go application, when this using this HTTP client, the basic HTTP client or the connection pool is being created, which connect to the Google server. Okay, so very simple. We are creating that HTTP client, and that connection pool is being created. And the first request that we send, it always go to the OS kernel. Okay, so the operating system kernel is responsible for doing the main TCP handshake and the DNS lookup. And after that, what happens is the connection establishment happens from the kernel to, using the network, from kernel to the Google server. Okay, the connection establishment happens, and it tells there in between the ACK, the SYN-ACK, everything is involved over there. And after that, what happens is, like, it tells that okay, the connection is established. Then using the HTTP client, we send the HTTP request to the OS kernel. So again, like, the actual HTTP request goes to the OS kernel, and from the OS kernel, what happens is, we do that get call to the Google server, like the get call that we just written over there, client.get. It happens by so OS kernel works as a middleman over there, and it happens to the Google server, and then it sends back the response similar way to the OS kernel only. So this is where that receiver buffer, the congestion control, the flow control, everything comes together during this exchange of data. And then when this HTTP response is ready to be processed by the OS kernel, then it sends back the data to the application, like to the HTTP, to the Go application via the HTTP client. So after this, using HTTP client, they send the data back to the Go application. That's all. So you see, overall, again, it looks a very simple operation, that there is a server, there is a client, and among the server client, this this connection is being established and some request response is going on, but there are multiple components are involved over there when from the simple application we are making the call. So as an application developer, we have to be very sure about these parts as well, like when we are sending the data from our HTTP client, is our OS kernel working correctly, or it is in a proper uh, in a proper receiver state to receive the data from the server end. So this should be one of our one of the few of our consideration while writing the code and thinking through the communication. So probably now you got a lot of idea, like behind that simple TCP connection, and when that REST request response model goes on, there are a lot of things goes. Like for example, there are things like flow control, congestion control, the ordering of the data, and even the receiver and the sender queue of the OS kernel. Everything comes in play and make the whole communication possible. So that's the video, guys. In my next video, I will be back with something related to the TLS or the security part. So far we have covered the UDP, TCP, the OSI layers. So these are pretty solid base of networking concepts. I'll be back in my next video. Till then, stay awesome.